Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is counting sub-multisets of a multiset, or what's as better known as counting combinations with repetitions allowed. This will involve counting integer solutions, the number of non-negative integer solutions to certain kinds of linear equations. So let's get started. Basically, in this talk, I will go through the whole issue through one problem, and then I will repeat it in sort of a more general context. But all the arguments will be given through this one problem. So let's say that you have 35 different types of donuts. You went to a donut shop. There's a whole bunch of types of donuts, and you want to buy some. There's unlimited supply of each type. You can get as many as you want. You're going to buy 13. Not necessarily distinct. You might want to buy all of them to be jelly donuts or something else, but you might want to also buy different kinds. And what you want to know, in how many ways can you do that? We want to translate this problem to several different versions. Again, in combinatorics, one of the things we like to do is be able to look at a problem from different perspectives, because all kinds of different problems might have the same kind of a solution. And if you can think of one problem from different angles, then you will note that if you saw a problem looking at as the other type is also the same kind of a problem. So this is the same as finding number of combinations when repetitions are allowed. So combinations is finding subsets. And here we're going to find a bunch of donuts, but we're allowing a repetition, buying the same donut over and over again. Another way of thinking about this is that given a multiset, find the number of sub-multisets of a given size. Here we have a multiset with 35 types of elements, the 35 donuts, and each one has infinite repetition number. This also can be a balls and boxes problem where we have identical balls, distinct boxes, and no restrictions on how many balls can go in any box. The boxes here will be the different kinds of donuts, and we have 13 balls that we're going to put in them, which is the same as deciding which 13 to buy. It will also turn out that this is going to be the same as the counting number of the non-negative integer solutions to certain kinds of an equation. And also, it will become counting the number of permutations of a specific multiset. And this last one is one that has been the subject of a previous video we know how to do, and that will be the way we're going to crack this problem, by translating all of them to a problem we've already done, which is finding permutations of a multiset, a very specific multiset. Along the way, we'll introduce the multi-choose numbers, this notation n multi-choose k, which will be a handy thing. This is a notation some people use, I use, not everybody uses, but it will be a good shorthand for what we want to do. Okay, so so let's say we had a set with 35 types of donuts, D1 through D35. And if I'd ask you how you would pick a subset of size 13 out of this set, and so here's when repetition is not allowed, just picking 13, the answer would have been, well, if that's the same as finding how many subsets of size 13 a set with 35 elements has, and the answer is 35 choose 13, which would be 35 factorial over 13 factorial, 22 factorial. My video on combinations goes over this quite a bit. If you're not familiar with the choose binomial coefficients and 35 choose 13, please watch that video first. But here the situation is a little bit different. I don't have a set of 35 donuts. I have a multiset. A multiset is just the same as a set, except every element is allowed to be repeated. Formally, it's actually a set with a function that for every element gives me a non-negative integer, its repetition number, or it's a positive integer. I guess the ones that are zero, you wouldn't put them in. In this case, I have a multiset where I have 35 types of elements, and the repetition numbers are infinite. They don't have to be infinite in this case because I'm picking 13. As long as the repetition numbers are 13 or larger, I'm okay. It's like it's infinite. I'm never going to run out. If the repetition numbers were like one of them was 5, or there was only 5 donuts of one kind left, then the problem would have been quite different, because then I would have run out of options of taking that as much as I want as for 13. And I'm trying to ask how many ways you can pick 13. And the answer is going to be this multi-choose notation, 35 multi-choose 13. So 35 choose 13 is when it's the number of ways that you can pick 13 things out of a set. 35 multi-choose 13 is the way that you can pick 13 things out of a multi-set with 35 types of elements, but with infinite repetition number. And our purpose is to find out what that answer is. Again, we read that 35 multi-choose 13. So M is a multiset with infinite repetition numbers, and we were wanting to find the number of sub-multisets of size 13, sometimes known as 13 combinations. The problem with calling it 13 combinations is that then you don't know, are you talking about a multiset or a set? The number of subsets of the subsets of size 13 of that original set, not the multiset, are also called 13 combinations. And so if you use the word 13 combinations for meaning combinations of size 13, and from the context, you have to tell whether or not you're finding that for a set where repetition numbers are 1, or for a multiset with infinite repetition numbers, or other kinds of repetition numbers. In this lecture, we're not talking about other kinds of repetition numbers. In later lectures, we will. So another way of thinking about the same problem is that I want the number of non-negative integer solutions to this linear equation, x1 plus x2 plus x35 equals 13. How is that the same? Well, x1 is going to be the number of donuts of type 1 I want to buy. x2 is going to be the number of donuts of type 2 I'm going to buy, all the way till x35, which is the number of donuts of type 35 that I'm going to buy. And I want the total to be 13. I want each one of these to be non-negative integer. I want them to be either positive or 0. And so finding how many solutions there are to this, one solution to this would be what is x1, what is x2, what is x3, what is all the way till x35, adding to 13. And any one of those solutions, which is the combination, which is the list of those 35 integers, would tell me exactly how to buy donuts, and vice versa. If I know which donuts I'm picking, I have a solution to this equation. And so the number of non-negative integer solutions to this guy is the same as the other question, which is how many ways can you pick a submultiple of size 13 from a multiset with 35 types of elements, all with repetition number infinite. And this formulation is actually really important, because lots of problems you can translate into finding the number of non-negative integer solutions to an equation just like this, a linear one with coefficients 1 equals something. This is also, you can think of this whole problem as the number of ways of placing 13 identical balls in 35 distinct boxes with no capacity restriction. The boxes, there's going to be one box for donut type 1, one box for donut type 2, one box for donut type 35, and I've got these 13 balls that are all the same. I'm going to put them in the boxes. Putting in the boxes is the same as choosing them. And so since there's no capacity restrictions, I could put all the balls in one box, or I could distribute them more evenly if I wanted to. But anytime that you place the balls in the boxes, you've decided which donuts to buy, and vice versa. If you know which donuts you're going to buy, then you have placed the balls in the boxes. And so there's a one-to-one correspondence between placing balls in boxes and choosing donuts, as well as non-negative integer solutions to that equation, x1 plus x2 all the way till x35 equals 13. The boxes, the first box could be x1, the second box x2, the 35th box x35. And so all of these questions, which I've not answered any of them, are the same. Now we're going to look at a different problem, a problem that actually on the face of it looks like it's different. So this problem is the following. How many words of length 47 can I make using 34 A's and 13 B's? 34 plus 13 is 47. And so I want to know, and by word, I just mean a string of letters where order does matter, but meaning does not. And so how many different ways can I put 34 A's and 13 B's in a row, and I call that a word? How many ways can I do that? Well, this is what a permutation is. So I want a permutation of actually this multiset, 34 A's and 13 B's. And I can solve this. This is, again, the subject of a previous video, but the argument is pretty straightforward. There's 47 spots, and let's decide where the B's go. As soon as you decide where the B's go, you know where the A's are going to go, because they're going to go to in the remaining spots. Well, we have 47 spots. How many ways can you pick 13 of them? And the answer is going to be 47 choose 13. So there's 47 choose 13 ways to answer this question. Why am I asking this question? This question doesn't seem to be relevant to our previous donut problem. And well, if you think about it a little bit, it is. But let's first make sure that we understand this. This is, again, number of permutations of 34 A's and 13 B's. If you think of this as permutations of a multiset, you may want to write the solution as a multinomial, 47 choose 34, 13, but that's the same thing. That's the same as 47 choose 34, or which is the same as 47 choose 13. So either way, because there's only two types, that the argument is very straightforward here. Okay, but I'm going to solve this problem that I just solved in a different way. I'm going to say, place your 34 A's in a row. The A's are all the same. I put them A1, A2 through A34, so that you know I put 34 A's down. And then what I'm going to do is decide where the B's go. So, and where are the B's going to go? Well, between these A's. So there's going to be some of them that go before the A1, some of them that goes before A2, some of them that goes before A3, some of them that goes before A34, and some of them that goes after A34. So I need to know what X1 is, what X2 is, what X3 is, what X35 is, which is how many B's go in any one of those slots. And therefore, what I need to do, and they have to add up to 13 because I've got 13 B's. So X1 plus X2 plus X35 is 13. And so the number of solutions, the number of non-negative integer solutions to this equation is 47 choose 13. And this was the problem that with the donut problem. This was the problem of you have 35 types of donuts and you want to pick 13. How many of type 1? That's X1. How many type 2? That's X2. How many type 35? That's X35. So I just solved it. The answer is 47 choose 13. So in other words, 35 multi-choose 13 is the same as 47 choose 13. And where that come from? It came from the fact that I started with 35 minus 1, which is 34, plus 13, choose 13. So the way I like to think about this is that you add these two up. If you want to find 35 choose multi-choose 13, you add these two numbers, 35 and 13, you get 48. You subtract 1, you get 47, and then 47 choose 13 again. Okay, so we solved the problem. Let's summarize this, what we just did. If you have a multiset with infinite repetition numbers and 35 types of elements, and if you have the equation x1 plus x2 plus x35 equals 13, and if you have the multiset 34 A's and 13 B's, then the following numbers are going to be equal. That's what we just showed. Well, first of all, 35 multi-choose 13, that's the answer of finding how many sub-multisets of size 13 M has. That number is the number of ways of choosing 13 elements from M with repetition allowed, sub-multisets of size 13. That was the definition of it. But it's also the number of ways of placing 13 identical balls in 13 distinct boxes with no capacity restriction. It's also the number of non-negative integer solutions to E. And it's also, and the key to cracking the problem is that it's also the number of permutations of W. That's what we just saw in the previous slide. And because of that, it's 47 choose 13, because that's how many permutations W has. And so the take-home message is that N multi-choose K is N plus K minus 1, choose K. Again, you add N and K, then you subtract 1 and choose K. And again, the way this came up was that we said, if you want, if you have N types of elements, put N minus 1 markers, and then decide how many, if you want to pick K of them, decide how many go before the first marker, how many go between the first and second marker, all the way, and how many go at the end, at the last marker. And you've got the N spots then if you have N minus 1 markers, and then you have to either put K things in among them. So you're finding a permutation of n minus 1 markers and k things that you're going to put, k other things, and that's n plus k minus 1 choose k. Okay, so now let's just say the same thing one more time, but this I'm just going to say things in terms of general numbers and not just 35 and 13. So n and k are non-negative integers. The symbol n multichoose k is red n multichoose k, and what is it defined as? It's the number of ways of choosing k elements from a multiset with n types of elements, and with infinite repetition numbers. And it's also the number of ways to select k object from a group of n objects when order is irrelevant. So we're not ordering things, we're just finding combinations, we're subsets, sub-multisets, and repetition is allowed. And also, 0 multichoose 0 is 1. You could think of that as a part of the definition, or you can actually think it true that if my definition is going to make sense, this is going to be the case. If I have a multiset with no elements and I want to pick none of the elements, the first question is that, can I do that? Can I achieve that task? You've asked me, here's a multiset that doesn't have any elements. Go pick none of these elements. And I will say, okay, I did that. I can do that. So the answer isn't how many ways I can do that. It's not 0, it's something. And it's 1 because if I do it or you do it, or if I do it on Monday or if I do it on Tuesday, I will always do the same thing, which is doing nothing. So there's just one way of doing it. Okay, so now what did we decide about this n multichoose k? We decided that it's by definition, is the number of sub-multisets of size k of a multiset with n types of elements and infinite repetition numbers. It's also the number of ways of placing k identical balls in n distinct boxes with no capacity restrictions. You can think of the boxes as the donut types and the D types, and the k balls, when you put them in, that exactly telling you which k elements to pick. So those are the same. It's also the number of non-negative integer solutions to x1 plus x2 plus xn equals k. x1 is the number of d1s you're going to pick. x2 is the number of d2s you're going to pick. xn is the number of dn's you're going to pick. We've made this argument now several times. And somewhat a little bit surprising, this is also, if you look at the number of integer solutions, is also the same as the number of permutations of n minus 1 a's and kb's. Again, you place the n minus 1 a's and then you have n spots, and you have to put kb's in them, and x1 is going to be the number of b's that go in the first spot. X2 is going to be the ones that go in the second spot, and my xn minus 1 is going to be the number of b's that go right before the last a, and xn is going to be the number of b's that go after the last n. And so the number of permutations of this multiset is the same as this, and because of that, we can actually know what it is. It's n plus k minus 1 choose k. If you have this many things and you want to find the permutations, this is the answer you get. We did the argument already. So let's do one final example and then we'll be done. Let's say that we have this equation x1 plus x2 plus x3 plus x4 equals 18, and we want the number of integer solutions, but we have the following conditions. We want x1 to be greater or equal to 2, x2 to be greater or equal to 1, x3 to be greater or equal to 0, and x4 to be greater or equal to 1. So unlike the case we had done, which we knew the answer is a multichoose, here I don't want all the non-negative integers. I want fewer of them. I want the ones that satisfy this equation. But not all is lost. We can do this pretty straightforwardly. So we can think of this as distributing 8 identical balls in 4 distinct boxes: the box for x1, the box for x2, the box for x3, and the box for x4. But then we have those conditions. We want to make sure that the box for x1 gets at least 2 balls, and the box for x2 gets at least 1 ball, and the box for x4 gets at least 1 ball as well. Well, do those. I mean, the balls are identical, so give those guys the thing they want. So give 2 balls to the x1, 1 to x2, and 1 to x4. You've got to do that, so do that. If you do that, you've used 4 of the balls. So now you've got 14 balls left, and you have to decide where they go. But now they can go in any of the boxes, and so what you want is the number of non-negative integer solutions to y1 plus y2 plus x3 plus y4 equals 14. The reason I'm using y's is because I really did a change of variable. Instead of what I did was that y1 is x1 minus 2. y2 is x2 minus 1, and x4 and y4 is x4 minus 1. If you put those, then I'm back to my original equation. But you don't really need to do that. These are just new variables that I need to solve. And how many in a non-negative integer solutions does that have? That's a multi-choose number. The answer is 4, multi-choose 14. Unlike choose numbers, unlike binomial coefficients, the top number can be smaller than the bottom number, because this says I have 4 types of elements, but I have infinite repetition numbers, and therefore I can pick 14 of them. And again, that's 4 plus 14 minus 1, choose 14, which is 7, choose 14, or 7, choose 3. So that's the answer to that. And this is the end of this lecture. And I will see you in future lectures on combinatorics.